Now, if we do this on the example that I'm using, we're going to hit a problem. And the problem is with the employee position title. And really, the reason is that there are many, many different entries in this title. For 10,000 rows, there are 400 unique entries. So that it will lead to a bunch of different problems, and some of them are numerical. It's just going to take, well, computational, it's just going to take a lot of time to run, but some of them are statistical. And the reason they're statistical is that we might have some rare categories. There's only one instance of architect 3 in the data set. We might have some overlapping categories. We have different instances of police officers, and the link between those instances is not obvious if we don't look at the string content, and if we just consider these things as discrete categories. And finally, it's a detail, but it's a real problem in practice. We might have new categories in the test set. So basically, one-hot encoder doesn't work well at all with this kind of data, and sometimes we have this kind of data. So the standard practice to do this is to resort to data curation, cleaning your data. It can be seen, it's mostly techniques from database normalization. And so one thing that we could do is we could do feature engineering, and we could try to separate the position from the rank, and maybe we could separate the position, the rank, and the department. So this would require us building rules that we might apply in pandas on strings to separate those things out. The problem is it's going to take a little while to build those rules, and they usually have to be handcrafted. Another related problem, for instance, in a different database, here we have a database where we have company names and we have the same company that's expressed under different names. Now that's a canonical problem of database curation, and it's known as deduplication or record linkage. And the goal being to output a clean database, basically to merge those different entries, those different entities, and represent them as the same entity. Now this is quite difficult to do in general without supervision. You usually need an expert that shows a set of mergers to have an algorithm learn how to do the mergers. And one problem is that it can be suboptimal, because here, the data set here, the challenge is to detect fraud with payments to doctors. And it's a real question on whether we should merge the Pfizer Hong Kong branch with the Pfizer Korean branch. Maybe they should be considered as the same entity, and maybe not. That really depends on the question at hand. So the problem with this view is that the goal is to output a clean database, which is maybe a question-specific point of view. What is a clean database? And in general, it's something super hard. So really, these things, all these IDs, are hard to make automatic and to make turnkey. And I'd like to claim that they're much harder than supervised learning. Supervised learning, so supervised machine learning, is a toolbox that works quite well as long as you have a supervision signal. Database cleaning is a hard problem, and you will need a supervision signal, but that supervision signal is basically a clean database. So usually database cleaning, you first have somebody clean part of the database, then you learn rule from this, and then you clean the rest of the database. So our goal here is not database cleaning, it's working directly on the dirty data and doing good machine learning on the dirty data. Really, the point being that the statistical questions, so the supervised learning problem, should inform the curation. And ideally, we should even curate. So the first work we did with Patricio Cerda, so I should stress that this part is really the work of Patricio Cerda, who's doing a PhD in my group. So the first thing that we did is that we took one-hot encoding and we relaxed it. And basically, instead of having zeros and ones, we added string distances between the representations of the categories, and we encoded with string distances instead of zeros and one. And that really tackles the problem of new categories in the test set, because if there's a new category in the test set that's not represented in the train set, I can just look at the string distances to the categories in the train set. And it also allows us to link categories. If, for instance, I have typos in my columns, which is something that does happen, the typos are going to give me very small string distances, and those two columns are going to look very similar. So there are different string similarities that we could be using. Maybe the most well-known one is the Levenstein distance. The Levenstein distance is basically the number of edits that we need to do to one string to match the other. And that's really a classic one. There's the Jarrah-Wilkler distance. It's the number of matching characters renormalized by the number of transpositions, character transpositions. It's well used in the database community. And there's what I call the n-gram or Jacquard similarity. If we define n-gram as a group of n consecutive characters, So for instance, if I have London, the first n-gram will be LON, the second n-gram will be OND, the third n-gram NDO. So we're basically taking all those n-grams. Here, these are 3 grams. We're taking all the 3 grams. And then to compute the distance between 2 strings, we're looking at the number of n-grams in common between the 2 strings and the number of n-grams divided by the number of n-grams total, okay? So if the 2 strings are the same, they have all the n-grams in common. So this is 1. So this is a similarity. If they're completely different, they have no n-gram in common. So this is 0, okay? So these are 3 classic string similarities. So because this is a Python conference, we're giving you a Python implementation. We have this software that we call Dirty Cat for dirty category, and it allows me to put pictures of cats on my slides. It's crucial. It's available online, BSD license and everything. It's something in between a research quality software and a production quality software. I think it's reasonably good quality. It's not as high quality as Scikit Learn, but it comes with documentation, examples, and everything. You can look at it. It also comes with example data sets. And it provides similarity encoding. So similarity encoder is just an encoder. It will work like Scikit Learn. You can instantiate it saying which similarity you want to use, and then you can transform the column of the data frame or the data frame you're interested in transforming. So it's a drop-in replacement for one-hot encoding in Scikit-Learn. Now, I'll show you how it performs on real data, but before I show you how it performs in real data, let me present another approach that is, it's been around for quite a while. That's called target encoder. It's not known well enough. The idea being that we're going to represent each category by the average target. So for instance, we're going to represent the police officer 3 by the average salary of the police officer 3 in our database if we're trying to predict the salary, right? So this gives us a 1D representation of all the categories. I've shown it here. So all our categories are embedded in one-dimensional, which is the average salary. So we have the average salary. And so you can see that in the database, the person who makes the least amount of money is the crossing guard. And the person who makes the most amount of money is the manager 2, actually. So by the way, this is maybe a bit surprising. The order in managers doesn't make sense, right? We have manager 3 who makes less money than manager 1 who makes less money than manager 2. Why is that? Because those are average salaries. And we might have people with different level of experience or I don't know what. It also is telling us that this signal is not a perfect signal. It's a noisy signal, this embedding. But it's useful because it's embedding all the categories close by when they have the same link to Y. So that's helping us build a simple decision function to do prediction from this representation, okay? Now, it comes with drawbacks. The first one is it doesn't know how to deal with a new category. If I tell you a category, if I give you a category that I've never seen, I don't know the average salary, I can't represent it. So I can represent it by the average salary of everybody, but that's losing a bit of information. And the other thing is it's absolutely not using the string structure of the category. So typos, for instance, it will not find the links between typos unless it sees enough of those typos to see that they basically link to the target in the same way. So I'd like to say really that it's a complementary approach to our approach. It takes a different point of view and is very interesting too. It's also available in Dirty Cat because our goal in Dirty Cat is not to sell the methods that we develop, but to help solve a problem, which is dirty categories. So it's target encoder, oops, and I was editing this too late yesterday evening, and target encoder does not take a similarity argument. So Patricia Serda did a numerical benchmarks on real-life data sets, here using 7 real-life data sets to compare the different approaches, and we benchmark linear models and gradient-boosted trees. And what I'm showing you here is the average rank of the different methods across the different data sets. So 1 would be that the method was always the best predictor across all the data sets. And so what you can see, and so there's more in the paper, we benchmarked many other methods, but I'm really giving the executive summary because many of the methods that we benchmarked were not helpful. So what you can see is that target encoder helps, so with gradient boosted trees, it helps compare to one-hot encoding. One thing that is not visible in those numbers is that gradient boosted trees do much better than linear models. So I would advise you to focus on gradient boosted trees in practice. They're much more useful for this kind of data set. So target encoding helps a lot. And then in the similarity encoding, what we found is that the 3-gram distance, the 3-gram similarity, was really the most helpful. And the others are not as helpful. So our take-home message is really we can focus on similarity encoding with 3-gram distance. Though it might be useful, for instance, to build a pipeline that stacks both target encoding and similarity encoding, because these two objects capture different information in the data. And that's easy to do, by the way, with a column transform. You just select the column twice and send it in the two different encoders. Okay? Now, in practice, we're going to hit a problem is that in many, though not all, databases, the number of different categories grows with the amount of data. Here, that's the second work that we did with Patricio, and we've gathered more data set, and now we've moved to 17 data sets. It's actually hard to find data sets that are not curated and with an open license. People do not like to share their non-curated data set. So please do share your non-curated data set. That's the only way we can develop better methods. So what you're seeing here is that across many data sets, as we increase the number of rows, the number of different entries that we're seeing in a given column increases. And increases sometimes very fast, sometimes only slightly fast. But it gives a problem because it means that if we're going to use the similarity encoder, we're going to blow up the dimension. And we're going to end up running gradient boosting on things that have 100,000 features, which is not only bad statistically, but also will take a lot of time. So really this is related to problems in, for instance, natural language processing, where as the corpus of the text gets bigger, the number of different words that we see keeps increasing. So it's quite related to classical natural language processing problems. So we need to tackle this. Elsewhere, we can't give this to you as a turnkey method that you can apply to large databases. So both similarity encoding and one-hot encoding are prototype methods. What I mean by prototype method is that they compare the data to a set of prototypes, and by default, it's all the prototypes on the training set. The challenge now is to choose a small number of prototypes to be able to scale. So we can take all the training set, that's what we're taking by default, it blows up. We can take the most frequent, but it's a strategy that's easy to game. You can easily have a data set that breaks the strategy. And one of the problems is that the most natural prototypes may not be in the training set. For instance, if my training set is made of big cat, big dog, fat dog, I probably want to break this in big and fat and cat and dog. And none of these original entries actually have the right terms. Okay, so I need basically to break down my categories. So now I'll tell you how we estimate those prototypes. And the thing that is going to save us is that when those different strings grow, they have common information. Here I'm showing you the growth in the number of 3 grams as I increase the number of strings. And what you can see is that it's a smaller growth than the number of different strings. And this makes sense because, for instance, if this dirtiness, this diversity of the string is made from typos, then typos actually modify a small fraction of the string. So yes, I will have new 3 grams, but most of the 3 grams will be in common. In practice, if I look at my data sets, you can really clearly see this, that the substrings are in common. For instance, in this drug name data set, I can see that I have many different versions of alcohol, but they're all versions of alcohol, so there's alcohol in common everywhere. In my employee salary problem, I have substrings that are really meaningful. Police is in common, officer is in common, technician, senior. So the challenge is going to grab this information and capture those meaningful substrings. And for this, we're going to use techniques from topic modeling in natural language processing. And we're going to apply topic modeling on substrings. So what we're going to do is that we're going to represent all the strings as their substrings using an n-gram representation. And here I'm showing a 3-gram representation, but in practice, we're doing something slightly more sophisticated than this. We're taking the 2 grams, the 3 grams, the 4 grams, and also the words that we've split with a set of separating characters that we have default values, but you can change them. So then we build a big matrix that represents each entry by its substrings, and then we apply matrix factorization on this. Really, matrix factorization, what it's doing here is to say, I will separate this matrix in two matrices. One matrix that is what I call the descriptions of the latent categories, and it tells me what substrings are present in a latent category. And another matrix, which is what latent categories are present in a given entry. Okay, so I'm really factorizing in the description of latent categories, categories that I'm inferring from the data, or prototypes, and how those are expressed in the data. So to give you an example of the result, this is, and so by the way, we're using the activation matrix, so the one that expresses which latent categories are in an entry. We're using this to represent the data. And so this is what I'm showing here. These are those employee salary, the employee position titles. And this is, and I've run the model with a dimensionality of 8. And this is the loadings that are showed. So what you can, if you squint your eyes, what you can see here is that it has detected something like a technician, like legal, police. It has detected those substrings, okay? And so one thing I'm not showing here that I should be is that we're using a heuristic to give a name to those columns. And the name is really what are the 3 words that are most represented in those columns. So this is useful because it's giving you feature names. We're encoding this with feature names. And so if we compare it to a similarity encoder, it's much more marked, much more present, much more interpretable. And then we can do data science, interpretable data science. And for instance, we can look at permutation importances of gradient boosted trees, for instance, with the categories that were inferred from the data. And this is what I get here. So what I'm showing you here is that I've inferred from this messy data, I've inferred latent categories that make sense and on which I can do an analysis and present it to you. And it also, by the way, predicts well. In the paper, we're showing that it gives you good prediction. Okay? So you don't have to clean your data anymore.